couple of housekeeping things. For those of you who have attended previous presentations today, this is the second or third or fourth time you've heard this, but we have online speaker evaluations this year that can be found on LEDucation.org. If you're attending sessions today, please go online and fill them out if you'd like to. It helps us keep the standard high, right, what people want in our speakers. So thanks for that. Also, if you have an AIA number and you need a credit certificate, if you have not done so after this presentation, please sign up outside at the table. If you are self-reporting and you need a CEU, you'll get, or an LU, you'll get that emailed to you at some point in the near future because you were scanned on the way in. For those of you who don't have a badge and were not scanned, sign the AIA sheet and you'll get a credit. Kevin Wilmorth has more than 34 years of experience in the application of light and product development. His background in lighting design led to executive positions in design and marketing for Visa Lighting, Kim Lighting, and Winona Lighting. He now owns his own product development company, which consults with manufacturers in product design, testing, and deployment, as well as offering his own products under the Tasca brand. He is also the editor of Architectural SSL magazine. Without further ado, Kevin Wilmorth.
Good. It's not quite afternoon yet. Well, I guess it is if it's right past 12, right? This course was basically motivated by, excuse me, instances where I've had either customers or customers of customers express their dissatisfaction with their meter reading. So they take a light meter out and they're pointing it around and they're saying, I don't understand, this is supposed to be 54 foot candles and this says only 45. And typically it's this, right? It's they're moving things around. And over time, I also observed that I had inconsistencies in metering results that we were getting, over the years, and what strategies we put in place to get rid of that so that I can trust what readings that I'm getting are within the bounds of what I expected them to be, right? So, and we'll kind of explain the differences between different kind of readings. So, all the boilerplate. So we're going to kind of go through what can we expect from a light meter, a methods for increasing to both the accuracy and precision, determine relative data as a valuable tool, uses of it, set up an affordable, small, informal lab. You could even do that. And then determine practices for tracking luminaire performances over time. So the first thing is, what's wrong with your metering methodology? Probably not using one. And that's actually what I discovered over time is we just weren't using one. And the other one is, we take meters out and we measure all this stuff, and the fact is there's a mismatch between what we see and perceive because our eyeball has got this pupil that adjusts. It's kind of like having a camera and auto exposure all the time. Camera's fine, so turn the lights down, camera's fine, turn the lights up, camera's fine. It's not really telling you anything. And the other one is that we have a pretty serious mismatch in different color temperatures, for instance, with how we perform visually. Cooler color temperatures or fuller spectrums tend to create higher visual performance, which really isn't necessarily related to the foot candle level that you have in the room or lux level. So these things have to be factored in as well. And then there's subjectivity, from it's too dark, no, it's too bright, I can still see you. There's all these factors that we can't use. You can't go to court and say, well, I went out in the parking lot and it looked like there was enough light. I don't know why she tripped over that irrigation feature. So we came up with meters. And the first meters we had were pretty simple because they're basically, excuse me? Oh, excuse me. The first meters we had were pretty simple because they're essentially voltmeters. What you've actually got is like a photocell creating a voltage, and then the meter just reads the voltage, and it says that it's foot candles, but actually it's volts. And it was good for the gold days of incandescent lamps. What's really interesting, these meters were horribly ineffective at measuring gas lighting. we meter to evaluate a product, we're surveying a lighting condition, we're kind of like verifying performance against a spec. There's a lot of reasons that we're doing metering. And with each one of them, there's kind of a different strategy to making sure you attain the best value, the best result. Sometimes you don't need, really hard line, everything has to be right on the money numbers. Sometimes you just need good relative numbers. Other times you need to make sure that you can back everything up, that every reading that you got that you're writing down has backing behind it. We measure illuminance, color, characteristics, modulation, flicker. You're probably aware of all these things that you want to whip a meter out for. So the first trick is, what do you want to measure? And that's where you would start off with looking for your hardware. There's no reason to have a soup to nuts, full-blown system that does full spectrum if all you really care about is foot candle levels or lux levels. So overbuying is something that happens all the time. We extrapolate from the data that we receive from the meters. We create things like, there's no such thing as measuring CRI or TM30RF and RG. Those are extrapolated from the data you collect with the meter. Those are not actually done by the meter itself. The reality is a digital light meter today is no more than a voltmeter either. It's either a current device, it's measuring how much current passes through the receiver, or it's a voltmeter. So all this other information we have to get from the data that we collect with the meters. By the way, in horticulture, it's got a lot of interesting secondary factors like PPFD and PAR, and there's some others that are kind of unique. So in every industry has kind of like some specialties in that regard. Machine vision guys are looking for different things than like architectural lighting designers. So the bottom line is that with the accurate objective data, we can make comparisons. So if you go take a meter reading and you go take a meter reading, if we're both getting accurate results, we should be able to meet in a room and have a conversation about our readings and trust that they are valid, right? Subjective variables are considered within the bounds of the real data. So in other words, how that impacts visual performance, how that impacts attractiveness of a display in a retail setting can be discussed. But if you start off with the baseline data being reliable, then you can have those conversations. If you don't have baseline data to discuss, then the discussion is just a discussion. You can't really lead to conclusions. And then perceptive variables can be factored mathematically, like we said in the visual performance, either from color temperature or illuminance levels, or if you're doing task lighting, it can be on contrast comparisons between the task, the ambient, and the surround. There's all kinds of derivatives that we do from the data that we've collected. So meters at work, we have to keep in mind that all the meters are measuring light within the visual perception. So they are not true like voltmeters, because if they were truly measuring photonic data, they would measure everything from infrared to ultraviolet, and all you would have is this big lump number that wouldn't mean anything. It wouldn't relate to us seeing. So all the meters are filtered in some way, whether they're done digitally or it's done with actual physical filters or the CCD configuration to match our visual response. So if you're really interested in photopic versus scotopic vision and visual science, you're going to have to buy instruments that measure photopic and scotopic as a separate setting, because the one that you're going to buy normally is going to be kind of like halfway in between. It's measuring visual performance at the center point, mostly scotopic, or photopic, excuse me. The other thing is, light meters that you buy that have the little white disc in them, or the little white dome on them, are all cosine corrected. In other words, they have this formula built into the way they're collecting light. So they are not spot meters. So if you put it underneath, yes, you're going to read different illuminance underneath the focal point of a spotlight versus the surround, but that's not a spot meter. Spot meter is primarily measuring luminance, right? How much light is emitted from the source. And most photometric light meters that we use, in lighting measurement can't really do that. So this is the core and kind of like the underlying part of this presentation is accuracy versus precision. So accuracy is how close a meter will reproduce a result against a fixed standard. So like you go to NIST and they calibrate a meter, and you take your meter and you have it calibrated to that, so that makes it accurate. It's accurate to a known standard. It's totally an objective standard set by somebody independent of yourself. Precision is how tight the readings are from reading to reading to reading. So if you look at it like diagram is kind of interesting because I don't know if this works. There we go. So in the upper left, the high precision, high accuracy is kind of like the goal. That's where you'd really want to be. But that requires a calibrated instrument to a calibrated reference. And who's calibrated the calibrated reference, and it goes on and on. But you have to have it traceable, right? So that's that whole NIST traceability is where you go back and they show you the paperwork and it shows you where was the reference source and how they came to that. Usually starts off with a mathematical ideal and it works forward. But the reality is that upper one in the upper right is where most of our meters are. Most of our meters, unless you're sending them out for calibration all the time, can be very precise, but they're not necessarily accurate. Because if they're not calibrated to a known reference point, then we don't know where that center point really is. It could be anywhere. Low precision, high accuracy, that basically means that it's kind of centered around the center, around the where it would be if it was calibrated, but its reading to reading results are all over the map. You can also get results from this from other things like flicker. 120 hertz sources will often give you this kind of weird scattered result because the meter is having a hard time reading the modulated light source. So sometimes it averages from the peak to peak, sometimes it's from valley to valley, sometimes it's from average to average, so you get readings that are all over. And you could have that happen on either one of those two lower ones. And then the one on the right is the meter you should throw in the dumpster. The low accuracy, low precision, right? If you can't get repeatability and it's not an accurate meter in the first place, it's time to buy a new meter. So there's your clue. These old guys, the reason that we don't see these anymore, these old analog $69 meters in your pocket 20, is they don't work. The selenium photocell that they had in them barely worked under incandescent light, and you'd be shocked that what the 70-foot candle levels we were designing back in the 1960s weren't. They were probably 150, 100. They were all over the place. None of these meters were calibrated. They're just little voltmeters with a selenium photocell. And when you try to measure an LED, you get really weird results because they can't see about a third of the light that the LED puts out because the selenium photocell cuts off at about 475. And if you look how flat it is from 550 down, it's kind of shocking that it measures visible light, reasonably well at all. So these kind of guys, these inexpensive meters, in my experience after testing a bunch of them, are actually you can find them that are quite precise, but they're not accurate necessarily because they have not been calibrated. They're calibrated to the factory that manufactured them, which usually has a pretty wide range of what their calibration data is. And I've also noticed over time that they slide over time off of that. So you can take a known 50-foot candle reference and then measure it over 3 or 4 years period of time by using the meter, and it goes 50 to 59 to 51, like that. It'll move around. They also don't take abuse in temperature and things like that. So you have to be careful of these things that impact both their accuracy and the precision. The higher end meters, like as you see the higher end, let's say a commercial grade, specifier grade product, this is the kind of meter you have to do, like we do expert witness once in a while, where you go out on a parking lot and you do the measurements and you have to go and stand up in court and say it's within within design standards, whatever, or there's no shadows on stuff. You have to have something that you can send to a like an NIST lab and have it calibrated. You have to have high accuracy and you have to have high repeatability or high precision. And that's why you pay the extra money for these types of meters. But you don't need that kind of meter most of the time. Most of the time, a precise meter is all you really need from day to day. You really need an accurate meter if you're doing expert witness. If I was a utility going to do before and after photometry, record keeping. If you want to make sure that a product is staying within its L70 specification, so you measure 50,000 hours down the road or whatever, and you want to make sure, you need to get as much accuracy into it as possible, because what accuracy does, it erases time. So if there's 3 years between taking 2 readings, if you have a meter that you've been using over that 3-year period of time, it'll slip. If you have a calibrated meter that gets calibrated every 6 months to a year, then 3 years from now, you can trust that the results are the same. So if the light levels are 20% of what they were, then you know that that's lumen depreciation. You can trust that, as long as you take care of some other variables. Other meters are kind of interesting. They're tempting, and I've been tempted from eBay to buy all kinds of meters and test them, and I've got garbage cans full of them too. The older quality light meters from the companies like the Minoltas and the Konicas and all those guys actually are surprisingly precise, but their accuracy is a little bit off, and they're hard to calibrate because nobody wants to calibrate the old meters. So they're okay for precision. You find that the repeatability is quite good. But you need to verify that against a meter that's known. So you almost have to do like an informal calibration, find somebody that's got a meter you can trust, and then test it against it and find out what its factoring is. Photographic light meters usually give you the wrong readings. There are like f-stops, or they're giving you numbers that are worthless. But they do have spot meters and stuff that are fairly affordable, and I'll show you a use for them that's kind of interesting. They're still usable if you have one. So if you're a photographer and doing lighting work, you can use your sometimes these meters can actually be quite useful. So this is kind of a comparison between an expensive meter and a cheap meter. And they track really well together. So accuracy-wise, they're relatively close to one another. Precision-wise, they both had about the same repeatability. So they seem to be about the same precision. If you look at it from an accuracy perspective, look at some of the older ones, they're all not too bad. But then you get down, like I said, you get down those old analog meters from the 60s and 70s, and it just falls apart. They're just not. That's why you don't see them, like I said. Nobody, besides, why would you want to? Those things are loud. They were $65, $70 back in the day. Nowadays, for $90, you can get a meter that's better than that. Color meter error is even worse. The older meters just don't get color well at all. Even the photographers are having problems with it. Under artificial light sources from fluorescent LED create really, really unpredictable results. So my advice on color meters is buy the best one you can buy, the newest one that's available. Because there's new technology going into the sensors, there's new technology going into the software that's interpreting the data, and there's new interconnections with like desktop software so you can do the interpretation. And it's increasing both precision and accuracy. What's interesting is, look at this was all normalized to the same light output. Notice that these two quality meters are still struggling with the CCT shift. They actually move a little bit under CCT. So CCT, in the old days when we had incandescent lamps and halogen lamps, we didn't really concern ourselves with that. When we had fluorescent, you just picked a lamp, so you didn't really compare a lot from the incandescent room to the fluorescent room and understand that the meter readings were not agreeing with one another. With LED, we're usually looking at a lot of different colors under different conditions fairly repetitively, and getting results that are this far off is kind of concerning. It certainly is to me. The LED, this is about meter error, this is kind of like combining accuracy and precision, is that you notice that the meter A lacks both accuracy and precision. D lacks accuracy, but has good precision. The flatter the line, the more precise the meter is. The more ramped the line, the less precise it is. So it's not like you're going to be using these tools necessarily, but it's kind of a comparison of technologies. What you kind of expect when you're in the market for buying a meter. App-based meters are popular, and the ones that we've been using they're great daily tools. Nice for collecting a lot of good data, a lot of data that I would have never imagined we could collect for the kind of money that we're spending on these now. And they're calibrated. You can get them calibrated from the factory every year if you want. And when they're calibrated, they're very accurate. They tend to shift a little bit over time, so they need to be calibrated. If you're going to do like legal work, if you're going to do real-life site survey work, I'd get these calibrated every 6 months. I'd probably have 2 of them. If you're doing it as a profession, you'd have 2 of them, one always out for calibration, one that you're using on a daily basis. One of the advantages of the remote sensors is I've run into troubles where the meters that have where you lay them flat and the meters straight up, is you get a lot of this interference of you in the picture. So I like separating the sensor from the meter so that I can set the sensor down and get out of the picture, right? It's also really good for other measurements, like if you're doing reflectivity or if you're doing transmission on materials, is being able to separate the head from the meter and get yourself out of the picture. One of the biggest problems I had as a consultant, or as a designer, we had a drive-through window at a bank, and they complained that they couldn't see through the glass, and we had all this lighting, and we were gonna make it so perfect so they could see through the glass. But the process, by the time we went from designing the lighting system to the bank opening, they changed the uniform color of the tellers. And they went from a light, kind of like a medium gray shirt to a white shirt. Now they couldn't see through their white shirt. It's the same kind of thing as, and remote sensing gives you the ability to kind of like set the meter up and get out of the picture. And if you want to put people in the picture, you can, but then you can stand back and you can say, why don't you sit down at your task and do your thing and let's see what the foot candle levels are doing. So if your head's getting in the way, things like that. Integrated meters are the ones that basically have a lot of, they're integrated, so you buy them as a unit. They got a lot of readings on them. Some of them just give you the digital reading like on an LCD. I don't find those as useful as the ones that do the graphical. Once you get into the kind of like graphical pictures of things, especially if you're doing TM20 or TM30, the graphical outputs and the colors, where the color point is on the CIE charts and all that stuff is really useful. The numbers really, and it's also really useful for showing a customer in the field, whereas with you showing numbers on a screen, not necessarily such a good thing. The only problem, like I said, is the ones that don't have a detachable head can be problematic, especially when you're measuring task lighting or areas with high intensity, because a lot of brightness coming off of you onto that meter can give you a false reading. I also like the ability, personally, of meter heads that I can mount on a bipod or a tripod and get out of the room and just set it up, and then I can get an X, Y, Z point in the room and measure from that point. The delivered data, we're now basically able to capture, and this is like, I've been in the business long enough, this is like, to me, magic. 90 parameters that we can look at plus, that we can look at on a one measurement. So you take one click measurement and you can get all this information from that one measurement. So if you take 10 or 15 measurements, you can take comparisons of everything, of all these things, from reading to reading, from condition to condition, so you can do your dim to white, and you can do your circadian studies and all that, and you can actually see metric results, like real-life numbers. And so that ends the conversation and turns it into a discussion. Lab meters, I use these actually more than most because I've got them, so you buy a tool, you're going to use it. But the other point is that a lab creates an environment in which you've eliminated every variable you can possibly think of. So you can take all the variables out, so now you're only measuring what the light fixture is doing or what a lighting environment is doing if you're doing a mock-up, things like that. And you're taking away all of the variables that create either fictitious or erroneous readings. The software interfaces too, not only do you get this 90 parameters, but almost all the meters today have the ability to plug them in USB port. You plug them into a computer, you load their software, and you can look at the data in graphic format as well as in digital format. You can export it in Excel spreadsheets and use it in comparisons. You can use it in a report. You can use it as future reference. You can put it in a file, and then, let's say you're doing the lumen depreciation study to find out what the hallways are. So you measure all the hallways and you pick all the points and you get 30 foot candles. You take all that data, you store it, then 3 years later you go back and check it. You can check all that data point to point by just adding a column in a spreadsheet. It's brilliant. Using the meters, again, accuracy and precision. You get accuracy by using basically using the same meter or calibrated meters for doing comparisons. You get precision by having a routine and making very, very certain and being very careful that you're eliminating variables and parameters that create errors in your output. So you can do photometric field verification, like a street light, for instance, but you're going to have to know the angle that you're measuring at. You're going to have to make sure that the meter is aligned normal to that incident angle, and that distance, because of the inverse square law, is critical. You need to know that distance within, hundredths of an inch or whatever. The more accurate this data, the more accurate the points you collect, the more accurately you can interpret the result you got from the meter. Does that make sense? Same thing with transmission. I don't use light sources for transmission as much because most of the meters will use any reference source, and then you put the lens over it and you can find out what its transmission is, and both the spectral as well as percentage. I usually use daylight, and I pick a nice sunny day and go outside, because then you can set a remote meter up. You set it outside where it's not being interfered by anybody. Just use the sunlight, because it's a nice full spectrum radiator, and drop the filter on it, and you get good data that way. And it eliminates a lot of the variables you get from having, well, is that lens or that product responding to, for instance, there's polycarbonates that have a real issue with short wavelength. So what happens, they're already clipping. So they're actually acting like a high-pass filter. So everything below 460 or 470 is being clipped. You can see that when you measure it under daylight. You'll actually see the dip. But if you measure it under LED, you won't see it, because the source doesn't have that much light there either, right? Reflectivity is one of these that everybody wants to do, but it's almost impossible to do really well, because if you use a meter and you point it at a surface and then you light the surface and then you try to measure the light source, getting the actual precision of having A and C and B being absolutely equal, making sure your incident angle and reflected angles are matched, and making sure that you're taking out any potential for the specularity of the source to distort the output, because a specular source will create a higher response at certain angles than it will as a flat source. So you end up doing it like at 15 different angles to make sure you're kind of like, reflectivity is a lot harder to do than it looks. There are actually meters made to do this specifically that have a fixed light source, and you slide the piece of material in, and it's comparing it to a white body standard. So if you do a lot of reflectivity standard, like if you're doing a lot of AGI 32 studies or where you're doing a lot of real good photorealism, you're going to need to buy one of these things. And you buy them from a paint supplier more than you buy them from a light meter, people. And it gives you the reflectivity and the spectral power distribution of the reflected light. We do this kind of thing once in a while. We build little simple gantiometers, and we use regular light meters mounted to the stand. There's no reason you can't use a light meter. It's just inverse square law. Candela divided by distance square is foot candles, so you can reverse all that math and create really simple. And if the lumen and the light levels are really high, we built this one for a customer, for instance, that just had really high brightness sources. So you just have to make the meter bigger. The bottom line is you're measuring light sources that are, let's say 1,500, 2,000 foot candles or less. 4 feet distance, you can deal with that, right? But if you're dealing with sources that are 20,000 lumens or like 20,000 candela or better, you're going to have to get away from it. And it's kind of like, and also large fixtures, if it's 4 feet long or 6 feet long or 8 feet long, to get good data on what it's producing, you have to get away from it, which in a way kind of messes you up in field measurement too. If you go into a shop and they're using big sources and you're measuring, foot candle levels, you need to make multiple readings to make sure you're kind of subtracting the effect that big sources have on that kind of measurement as well. Relative measurement is the thing that I think gets misunderstood, but it's the one thing that we use the most. So relative measurement is where you're just basically comparing one thing to another. So, this source versus that source. You don't need accuracy for this. You don't have to have a meter that's perfectly calibrated and accurate. You just need one that's repeatable, precise. So you can do, like, in this case, you take known source, you got one, and it's 600 lumens from whatever reason. The manufacturer told you so. So manufacturer A said it's 600, manufacturer B goes, ours is 700. So can you compare those two? Well, you can definitely compare what A does versus B. So you can say A, assume it's 600 and measures 30-foot candles at 2 feet. B measures 36-foot candles at that same 2 feet. So you can factor the two of them. So one of them you can say if it's assumed 600, then the other one is 720. So you can do a relative and just do the little bit of a math and compare one source to another as long as you have good precision. If you have an imprecise meter, all you're going to do is know that the meters are imprecise. So you need a precise meter, don't necessarily need an accurate one. Another relative one is like an integrating sphere. For instance, in this case, I just used an old meter that had a broken head, created a new photoreceptor that went into the sphere, which came from, I don't know where. It was another thing I had on the shelf kind of thing. But the fact is, it doesn't matter. I put in a reference source that I knew was 322 lumens, and that was an NIST source. Read 157 on that meter, so I can use that factoring of 2051 to all the other readings I do for a similar light source, right? So it's a relative measurement. All I need is precision. I don't need accuracy. But if I were to do this for a customer who wants to know exactly how many lumens this fixture's putting out, you would absolutely have to have an accurate, calibrated meter. Otherwise, you get. So this is a relative spot. This is what I was saying about using a photometer or photographic meter. I just use exposure value and compare different points if I'm just trying to figure out what contrasts are, right? So you got A, B, C, D through G. So A to C comparison is a 1.4 to 1 all the way down to 1.1 to 1, I think was A to F. So you got the light directly in front of the person sitting at the task versus the ceiling above the partition versus the partition in front and to the side. So you can use virtually any meter for these kind of relative measurements and comparisons and contrast ratios. It works just fine. Nice thing is with the photography meter, it has a 1 degree field, so it's not looking at the whole ceiling, right? The common metering areas, a lot of us assume that meters do something they don't. It's hard sometimes for new people to lighting, and even some people that have been around for a while, to understand that light meters don't measure photons. It's not about that. Everything we do, light is converted to electrical energy of some description or resistance through some digital component, and that's converted into a reading that we call a foot candle or a lux. But it's going through a lot of translation, and that's why it's important to trust the meter that you bought and trust and understand where its limitations are and where its strengths and weaknesses are. There's also the observer interference we talked about. Wrong meter setting, that's another one, fairly common. Push the little buttons because they're not always auto-ranging. So you're getting the 1.33 on the meter head, but you didn't notice up here it's an exponent of 2. And then poor equipment condition and lack of calibration is probably the fault of 90% of us that have meters laying around. If they haven't been calibrated in a year, they're not accurate. You can just assume that. They're not accurate. If they haven't been calibrated in 3 years, they're definitely not accurate. So you can check their precision and assume that you can use them for relative measurements with precision, but never assume that a 1 or 2 year out of calibration meter is accurate, because it's probably not. Heat, vibration, just being used, and all battery condition. The other one is not being used is just as bad form as using them all the time. So in field measurement, the things that I think give you the best results are, this is the one mistake that we go out in the field and we take our little notebook and we walk into a room and we say, yeah, 50-foot candles. Walk into the next room and where in that room, in what relation to the lighting fixtures that were in that room, were the blinds open or closed, or how many people were standing in the room and what clothes were they wearing, and what is the office furniture and stuff. So when we do, if you do a metering for, like, if you're looking at lumen appreciation, you take a map of the room, take the tripod out, you put the meter head on the tripod, you set it in an XY, you set the Z point, take the measurement, then take a photograph of the room with your phone and attach it to this file. Because if you're going to come back 3 years from now and you've got a customer complaining, I think we've lost more light, and I think these LEDs are not holding up to their 50,000 hour or whatever, and they've just painted the room black, I had a massive disaster on a project where we did 5 inspections on the project, and all the wood in the space was all dyed, like white, 1980s, where they do the bleach, all the bleached wood and all that. Then the interior designer gets fired. They hire a new interior designer. They come in, and I'm expecting some changes to the space. And I get a call from the owner, and he's really angry because the lighting wasn't good. He couldn't see in his kitchen. Well, the lighting designer painted all the cones in the fixtures black and stained all the wood in the place black. We called it the Monster House. Well, same thing. So if you go out there and the customer's complaining about lighting quality, if you don't have any proof that conditions have changed that are causing that meter change, that reading change, then it's your word against theirs. And that's, good metering is about good metering, and data collection and data storage and archiving is about eliminating that. So I do, you got a simple map, you say 30 feet center of the room, 30 inches off the floor, center of the room, 55-foot kennels. It can be handwritten, it doesn't matter. But you need the map, you need the photograph to go with the map. You need to even, if you've got data on what the wall paint finishes are. I've even, at different times as a designer, it's actually written down what the spec was on the paint. Because you can walk in and it looks like the same room, it looks beige, but you don't realize that they painted it twice since, and the beige that they've got on it now is 2 shades darker. Well, if a lot of the light, if it's an indirect lighting system, you could actually lose 15 to 20% of the light on that reading spot, right? Just simply because they changed the color of the walls by a little bit. So good record keeping. We always have, how many of you, are using Excel spreadsheets for other purposes, right? So we create a lot of Excel spreadsheets showing, and we've actually started building classification systems where we classify products based on their CCT variability. We classify them based on their, quality, other quality, like CRI or TM30, and keep track of this manufacturer's product was delivering this light level, but also here's the other of those 90 parameters. Here's a sampling of the other 90 parameters that we collected on them, and we put that on our logbook too. And we start noticing trends, right? Certain manufacturers have very consistent, let's say, precision, right? From fixture to fixture, they tend to have the same kind of performance variables or values, and others are all over the map. So it's a way to kind of keep that logbook for yourself, using metering and metrology to give you that core so that you've got good data that you're using. Now when you say to the manufacturer, yeah, we're not using your stuff anymore. And it's because the last 2 tests we've done show that your limit appreciation is lower, A, and B, we find your CCT shift is unacceptable. If you just do that as an opinion, you know what that manufacturer does with that information when he leaves your office? Blows it off. Ignores it. But if you hand him data sheets and say, this is what we this is what we, sorry about that. This is what we measured. Here's the data set we collected. Here's what we just measured in the data set we collected, and we can tell you that nothing happened in the room. It's your product. He can take that back to his engineering department, and they can throw it away, but or use it. So one way or the other, it's probably going to get it up in a can, but at least what manufacturers can be trusted, right? Tools and accessories, like I said, the tripod monopods are good. Tape measures, levels and protractors, we just do it on the phone now because that's pretty cool, and they're calibratable. Little pieces of string, color checker cards. The color checker cards and gray cards are interesting because it's hard to tell when you're looking at a wall, the coloration of a wall. If it looks, beigeish, that's fine. But sometimes it's really hard to tell how much towards the non-reflective state it's become, right? So if you use a gray card and you hold it up and you put the meter head on a bipod and aim at it, you can put the gray card up and then pull the gray card down, and you can see relatively to that 50% gray card what the reflectivity is on the wall, and it gives you another data point to write down. Another one is reference sources. I collect them over time, sources that I found to be very accurate or have come from independent labs or even have been tested against an independent source. And you just keep them around so you can use them to test against something else, right? So a new source comes in, you've got something to go back to and say, well, this one was pretty close to 600, let's see how this one really is. Temperature meters with LEDs is critical if you have any field service interaction. So in other words, if you're looking at problems you've had in the field, or if you're looking at performance variabilities that don't seem to make sense based on the product, and it seems to be an application thing, you need temperature meters to find out whether you're doing it to the fixture because of where you put it. The number of light fixtures that are put in duress by the specifier putting it in, or the installer putting it in such a way that it puts the fixture under stress, is quite high right now, because everybody's smaller, thinner, skinnier, so they're taking these little linear fixtures and jamming them in coves that are just too small. So if you go out in the field and it seems things are shifting blue, or your lumen output isn't where you thought it was going to be, or the brightness, whip out a light, even if you've only got a single channel thermometer, and stick it on that heat sink. If you start seeing numbers in that 50 C range or higher, 50, 60 C, then you know you're the one that caused, or the installation has caused the problem. The other one is at end of life, you'll also find some interesting things. At end of life, as drivers reach the end of their life, they also can get hotter. So you can also end up in problems where the fixture's behaving badly, take a temperature reading to it, and you're like, wow, this thing is 90 C. When we first installed it, the highest temperature to go out was 45 C. That's an indicator you've got another electronic failure happening. So it's another point, that's not lighting, but it's certainly important to it. The non-contact IR meters are junk in the lighting industry. They're worthless. Most people don't understand how to use them. The color of the surface, the material that the surface is made out of, all of that has a huge impact on what the meter reading is. So if you shoot it at a black extruded aluminum heat sink, and then you shoot it at a cast aluminum head that's not been painted, then they could be exactly the same temperature with a contact thermometer, but when you read them with the infrared, the black extruded one will be a higher temperature than the cast one. They're impossible to use. You certainly can't use them by aiming them up in a light source at the LED, because the light that an LED puts out does have a little infrared in there, and that gets read by the meter. So avoid the kind of like, it seems like a great idea. You could buy one of these $100 non-contact IR meters, and boom, you just point it at the heat sink. The silver heat sink is different number than the black. Flicker checker, I've got two philosophies on flicker. My personal philosophy is you can see it, it's bad, don't do it, right? Don't use it, bottom line. So I created this, and there's also been the one for Motorola. I think Osram had one at one point. Same thing, it's essentially the little spinny wheel thing, and you drop it as a top on the table. If you can see flicker in these, in mine, and the one I use color because I like rainbows, right? So if you see the rainbowy effect, there's flicker. And to me, that means don't do it. Don't use that product. So that's one way of doing it. It's kind of like you use that subjective view of subjective verification of flicker, and then you have a binary decision. If flicker exists, don't use the source. If you want to get more finite and say that, you can use, there are flicker meters, and a lot of meters today are starting to introduce flicker as a component within some of their 90 parameters that they collect. But the problem is you have to understand what the metrics are, like Fmag and frequency, VFMA, percentage index. What metrics are you going to use to evaluate the product? And then what are you going to set as your thresholds? And the IEEE and IES are both working on a kind of like a standardized, flicker risk factor table, so that'll help. And these flicker meters can help you get there. But honestly, I don't care what the metrics are. If I see it, it's bad. The reason it's important to know these parameters and the more finite is because they're finding out that even invisible flicker has a non-visual performance impact. So even if in the room that the people say, I don't see flicker, they've done tests to show that with certain flicker characteristics, their performance, their visual performance, acuity, speed of reading, things like that, go down. So that's why you would need this. So if you're doing more finite science, right? And if you're doing any kind of science studies, obviously, walking in here and spinning the top isn't going to go over really well. I haven't tried it, but anyway. And then the other one is subjective color reference, is whether you use a box like this or multiple MR16s on a rack or just have them in your pocket, it doesn't really matter. But being able to take samples and say, so you got an interiors customer or you have an architectural customer saying this thing doesn't look right underneath the lighting, that you can double check his samples underneath a known reference source. So you click it over to 3K or 5K or whatever and see what it looks like, and then go out in the field and look at it. And you could actually take a box like this and put it up against the wall and flick it. You can tell whether you need to do some more measurement of the lighting that you put in versus what you expected it to be based on, you know, like a uniform standard. Does that make sense? And you can look at color cards, you can look at their samples. You know, they give you the brick samples, or the interior designers do their color boards. You can do all of that. So you can do it ahead of time, then you can use it in the field to verify that you got what you wanted. So in a way, this is kind of a meter, it's a subjective meter that gives you relative performance between a reference source and the actual, without using numbers, right? Other than the ones that are written on the box itself. So I like this one. Any intellectual fool can make things bigger and more complex. It's a touch of genius and a lot of courage to move in the opposite direction. And I'm going to just simplify that to just keep it simple, stupid. I mean, the reality is define what you're trying to do. So if you're an electrical contractor and you just want to make sure that the lighting output is where the customer expects it to be, then you don't need a whole bunch of color parameters and things like that. You just need to make sure good verification. If you're doing surveys where you want to know, you know, everything from human factors studies to, you know, daylight contribution, impact on color. If you're doing some really in-depth studies, you're going to have things that cover more parameters. If you're doing things that have to be legally bound, that could be legally binding. Either as you're held to accountable for this performance, you're going to hold the manufacturer accountable for performance, or you're going into court, or you're doing a utility before and after, that kind of thing, then you need things that are both accurate and precise. But you don't need to spend $15,000 on the best meter there is in every case. So that was my kind of like top view of this. Is there any questions? Comments? Oh, come on. I'm sorry again?
Will you email the deck?
Yeah, I think they also make it available on the website. Yeah. Yes.
You mentioned a little bit about spacing of the sensor to the light source.
Yes.
Can you go into more detail about, I guess, different setups, what's a good practice for how far you should set for like 2x2, 4x2?
Oh, I see.
Like if I'm making a little setup.
To do like a little ganniometer kind of thing?
Like a little, you know, like a crate and just paint the inside black.
Yeah.
Try and set up the reading sensor, how far apart should it be? Is it going to miss a lot of these too close?
The ratio, I mean, ideally, you want to be around 10 to 1 from the longest distance from its center point. So if you're pivoting it around the center and it's 4 feet long, that's 2 feet. You need to be able to get 20 feet back from that to get a good measurement.
Okay, so the length, the diameter of the light source.
Right.
10 to 1 for that.
So the radius from the center of your pivot point, right. 8 to 1 will work, but you have to be cognizant of the fact that that inverse square wall works against you. As that fixture pivots towards you, that one end of the tube is getting closer to you. You know, so you could actually do it at 4 feet and do a spreadsheet that took the inverse square law into account and took that out. You know what I mean? Sure. Yeah.
Do you ever measure vertical illuminance, and what are there any special challenges and recommendations that you have to overcome that versus horizontal or like a surface?
Yeah, taking vertical illuminance meter readings with an integrated head on a meter is going to be really tough because you're going to be in the picture. So with a remote head, then the thing is to get everybody and everything out of the way that doesn't have anything to do with the measurement, right? But yeah, vertical is 10 times more complex and more difficult to take care of the variables than horizontal. You know, horizontal, you just lay it down and walk away. Vertical is as soon as you stand it up and face it out, you're like, okay, wait a minute, now I'm just taking a picture of my shirt. Yes?
What was the device that you said was more readily available from the paint store?
They've got it's a little box. You can find them on eBay too. They're a little box that has It's a like they call them reflectometers. There's other words for them. They've just got a little sample. Usually it's a little white card that's already in it. Then you put your paint card inside of it and it'll tell you what the reflectivity is. Some of them, actually more sophisticated ones, give you a reflected output by color. So they'll help you with the reflective. You can also make your own, kind of like what he was saying with the black box. If you take a cardboard box and paint it black, put your meter on the top, and put a white card and a light source right next to it and put a white card underneath it, you could measure a white card and then measure sources against that. All right, thank you very much.